So for the past couple of videos on root locus, we've been talking about root locus just in the context of a proportional controller in a feedback loop. But we can use the root locus tool for any parameter design that we would like. So what that means, if we're trying to affect where our poles are, we don't need to have a fancy control system with a sensor and a meter. We can use the root locus math to determine what size mass we would want in a mass spring damper system, or to determine how large of a damper we'd need, or what size vat we would need in a fluid system, and see the effect of our poles on changing a given parameter. So we're still going to be fueled by that concept of 1 plus k GO of S is equal to 0, which is what we got from a feedback loop. But we can manipulate any characteristic equation we want to this format to see the effect of changing k from 0 to phi. So I will write that down for you. So we can manipulate any characteristic equation, where characteristic equation is setting our denominator of our equation to 0 to find the solution and find our poles. To see the effect of changing k, and k doesn't necessarily have to be k. We're going to look at a mass spring damper system where we change k, damper, and mass all from 0 to infinity. So I'll write that as changing the parameter. So let's start off with an example of a mass spring damper system. So we're going to have that standard mass spring damper system that we've seen a while. We're going to say we have a mass that is supported by a support that has damping and elastic properties, and it's governed by the equation it's governed by the equation k over ms squared plus bs plus k. So our characteristic equation would be ms squared plus bs plus k is equal to 0. And what we would want to do is we want to manipulate this characteristic equation into the root locus form. And I'm going to say, instead of 1 plus k, since we have a k as one of our variables, we'll just have p GO of S is equal to 0, where p can be any parameter. So what I want you to do is I want you to figure out, for a given parameter, and that's just a variable that we have control over, so we have k, b, and m for this example. What is our open loop system that we get if we have that as our equation? So if we manipulate the equation into 1 plus p GO of S, and we say that the parameter we want to isolate is going to be k, b, or m, what we want to do is we want to figure out what GO of S is so we can plug it into a root locus on MATLAB. I'm going to write root locus, and so that's just our locus of system in MATLAB, where system is equal to the transfer function of your num den, and the numerator denominator is equal to our GO of S. So go ahead, pause the video, and when you are all set, there's a little possible, just check your GO of S with mine, or you can watch the K example first before moving on. Okay, and I just recalled that MATLAB code, so if you want to, I moved over the text a little bit. So we have system is equal to transfer function, numerator, denominator, root locus is system. I'm just going to draw these on this board, but you can verify later on. So if our parameter is k, we want to have the equation ms squared plus bs plus k manipulated into the format 1 plus k times GO of S is equal to 0. So the way we would do that is we would take the values of ms squared plus bs and divide the whole equation on both sides by ms squared plus bs, which would give us a 1 plus k times 1 over ms squared plus bs, and that whole equation is equal to 0 divided by ms squared plus bs, which is still equal to 0. So in MATLAB, for our numerator, we would just type in 1. For our denominator, we would type in m space b space 0, because we have 0 times 1, and we have m times s squared and b times s. And if we put in the root locus format, then root locus, it always starts off at our open loop systems. So here we have a pole located at 0, and we have a pole located over here. And what happens is if we increase our k value, we're going to have two poles, and I'll draw them in different colors, but which one goes where doesn't really matter. Just MATLAB likes doing two different colors to show what's happening with each of them. So now we have that there's two poles, and as we increase our spring value, we can start to have an underdamped system, where if our spring value is low, we have an overdamped system, which we could expect because the damper is much larger than our spring. And as the spring gets higher and higher, it becomes an underdamped system, but that damping value will always be there, so that won't change. Our time constant will not change, because our time constant is determined by b over m. So as a result, or m over b, because tau is related to 1 over, but it's manipulated by that b over m, so it's not affected by our k. So we can see that in our root locus. So now I want you to go through, find the open loop transfer functions for if we're manipulating with b, and if we're manipulating with m. I'm going to go ahead and redraw this root locus so it's a little bit smaller. Okay, so I talked for a while, and then I realized I never pressed record, so hopefully I am picking up at the part where I stopped. So now if we want to see the effect of changing our parameter b, then we are going to have s, since we are going to take ms squared plus k, we'll divide by both of those terms to have 1 plus b times that s term in the numerator, so our numerator in the transfer function would be 1, 0, and then divide by ms squared plus k. So if we draw, we're going to have a 0 located at 0. We're going to have an undamped system for our open loop, because at the beginning, when b is equal to 0, we have an undamped system. As we increase our value of b, our system goes from being underdamped to critically damped to overdamped. And we'll have one pole will go closer to the origin and approach the origin as b gets close to infinity, and the other one will approach negative infinity. So it starts to act like a first order system as that damping value gets higher and higher. And this makes sense because we start off with an underdamped system. An undamped system, as we increase the damper, becomes underdamped, then critically damped, and then overdamped. And finally, if we increase our mass, we can say that we will have s squared over bs plus k. So s squared over bs plus k. And so we're going to start off, and I'll draw this a little bit over here, where we have two zeros, both located at 0, and we start off with a pole at negative k over b, because that causes our characteristic equation to be 0. So when a root locus is drawn, and this is something that you don't really have to know, but we have it that it will start at a pole and either go towards infinity in some direction or end at a 0. So in this case, we have a second order system, but our open loop system starts as a first order system with two zeros on top. So we're actually going to call in a pole from negative infinity. So what that will look like is we'll have a pole come in from negative infinity. At a certain point, it will go and close to a 0. And then I've used orange before, but I like purple and orange. Then we'll have our other pole will start at our open loop pole, and our closed loop pole will, as it increases, meet up with that pole coming in from negative infinity, and then loop around and end at the other zero. So if we have a very small mass, we end up with a system that has somewhat strange properties, but then as we increase that mass, our system will either be overdamped, and then once it gets small, as it gets larger, it'll start to become underdamped, and then the larger it gets, the slower our settling time is, because the greater our tau value is. So when we look at our root locus, we can see the effects of changing that on the results of our closed loop system, which, even though this isn't a feedback loop, we still use the terms open loop to refer to that GO of S, and we use closed loop to refer to the pole locations of the full system, which in this case is ms squared plus bs plus k, and we can manipulate those pole locations by manipulating the values of m, b, and k. So that isn't new to us from before this week, but what is new to us is that we can actually visualize how it changes using this root locus plot. So that's how we can use the root locus plot to see the effects of any parameter on our overall system.